Good morning, good afternoon, and good evening, everyone. So today we're just going to be continuing basically the exercises we did. um, so last time we stopped at number 8. So here, so we're given two vector functions. So they have different parameters, one's t, one's s. And we want to determine the ordered triples or points in which these two curves intersect. And so we were able to do that. So the first thing we did was we equated the two curves or the two vector functions. And so we equated each of their components, their corresponding components, the x, y, and z. And then we solved for s and t. And we were able to get a point in which both of their paths intersect, which was 1, 4, and 49. And then we were being asked what's the angle of their intersection. So it's kind of similar to this diagram where we have two curves. These are not, by the way, the exact curves, but hypothetically we have two curves. They intersect at this point here. And from there, we wanted to, or our strategy was to find the corresponding tangent vectors of the two curves and then find their angle of intersection. And so we were able to do that. We had a formula for doing that when we get their vectors and they intersect, and then we find that angle in there, and we found it to be approximately 41 degrees. So yeah, I made the mistake actually here. Here was my mistake. So if you watched my last video, I made this into a 5. It was supposed to be 6 because that's square root of that's 4 plus 1 plus 1, so that's square root of 6. Yeah, and then the rest is good. So that was my mistake. So anyways, that was me talking about derivatives of vector functions. So moving on to our next example here. So for our next example, we have number 10. Don't know why they skipped number. Anyway. Okay, anyways. So here we want to find r of t. So this time it's the reverse. We're given the derivative and we want to find the actual vector function. So here the derivative of the vector function is given. So we have it in ijk form. Let's just write it out. 60 to the 5th j plus plus what's this? Square root of t k. And we're also given a point here. So we're given r of 1, which is equal to I plus j. Okay, so the way I would do this is to translate all of them into vector form first. That's what I would do. So I'm going to say translate all of them. Or not really translate all of them. Translate all of them, yeah. I'm not going to write all of them. Translate to vector form. So here we see r prime of t, the derivative, which has these components. So here, this is also for my sake. I'm just translating everything to vector form. Also this r of 1, which is I plus j. So that's basically 1, comma 0, comma 0. I'm going to add that to 0, comma 1, comma 0. So that's 1, 1, 0. Okay. So now what do we want to do? We want to find R of t. So we want to integrate. So there's a calc2 thing. So we want to integrate to find R of t. Right? Because if we integrate this thing, our derivative, we get back our original position vector. So that's what we want to do. So let's integrate. So if we integrate r prime of t dt, then we're also going to integrate its components. So we're integrating 3t squared. We're integrating 6t to the fifth. And we're also integrating square root of t. So let's quickly do that. Okay. So just like differentiation or getting the derivative, we also have some rules when integrating. So that's going to be, let's say the first one, right? Okay. So for the first one, well, here we're just going to put the 3 out because that's a constant. And we're left with t squared. And here we just get the antiderivative by adding 1. So there's another property. How do we know if this is correct? Well, we take the derivative of t cubed over 3. And that's how we'll get it. And actually, this is correct because 1/3 t cubed, if we take the derivative of that, that's 1/3 times 3 t squared, which we just cancel, so we get t squared, which is what we originally had. So we know that this makes sense. So if there are techniques for getting the derivative, there's also techniques for getting the antiderivative or when integrating. So yes, here we have t cubed over 3. Here we get some constant, right? Then here we have t cubed plus some constant. I put sub 1 because there's also going to be some constants in the other derivatives, so I'm going to consider that. But yeah, the reason why there's a constant is we want to consider that general case. We want to make it as general as possible because when we take the derivative of a constant, it's always 0. So we just added that constant to make it more general. So that's that. What else are we given here? We're given R of 1. Don't know how to do that. But yeah. Let's look at 6t to the fifth. So again, we take out the 6 because that's a constant. Honestly, this is also a review for me for integrating because I kind of forgot it a bit after only having done it for like 3 weeks ago. I totally forgot this thing. Then I got 6 t to the 6 over 6. Oh, look at that. I got t to the 6 plus c2, some constant. Then here we get t to the 6 plus c2. And let's do the last one. So we have square root of t dt. So here we can, again, when we're doing derivatives and integration, well, usually we want to put them in fractions. We want to usually get rid of that square root. And so if we do that, well, now we can integrate this thing. So here we're adding 1. So it's going to be 3 over 2 over 3 over 2 plus some constant. And here we have 2 over 3 t 3 over 2 plus some constant. Okay. Now, what do we want to do? Well, usually after integrating, we want to find these constants. And so the way to do that, okay, let's actually try to rewrite it. So R of t is now these guys. So t cubed plus c1 t to the 6 plus c2, and then the other one, 2 over 3 t to the power of 3 over 2 plus c3. And now I want to find that constant, or constants. So find constants, c1, c2, c3. How do we do that? Well, we use the other info we have. So this one, we make use of that. So I guess we can equate each of them, get their constants. Okay. So here we see r of 1. Use r of 1, which has these vectors, right? And so we say, oh, well, d cubed plus c1 should be equal to 1 when t is 1, right? So we say, okay, when we do 1, when we do r of 1, d cubed plus c1 becomes 1 cubed plus c1. And this is apparently equal to 1. So here we say c1 is 0. Right? So now we found our first constant. Next, we have the y component. So here we plug in the 1 to the 6th power, plus c2. This should be equal to 1 again. And so c2 is again 0. And lastly, we have 0 for our z component. So we plug in 2 over 3 times 1 to the power of 3 over 2, which is just 2 over 3, plus c3. This is apparently 0. And so here we have 2 over 3 plus c over plus some constant is equal to 0. So that means the other constant is negative 2/3. Okay. And so after finding the constants, well, we can just plug in like normal. So we have t squared, I believe, for the first one. No, t cubed. So we have t cubed for the first one. For the next one, we have t to the 6th. And for the last one, we have 2 over 3 t to the power of 3 over 2 minus 2 over 3. Notice I didn't include the plus zeros anymore because it doesn't matter. And so here's our position vector. So that's really what integrating is. We just get the reverse. Yeah, looks clean. I could do this in IJK format, but I really just have to add IJK to it, and that's it. But I prefer not to. I mean, I don't need to, at least. So I'm not gonna do it. Let's see if I got it. If not, we'll see first. We'll see. T to the 6th. So t cubed, comma, to the 6th, comma, 2/3. I feel like I know where this is gonna trip me up. It's the fraction thing. E to the power of 3 over 2 minus 2 over 3. Okay. Let's see. Let's see. And yes, we got it. Okay, last item for derivatives and integrals of vector functions. So here we find, so again, we're trying to find r of t. If our given derivative, or our prime of t, or tangent vector, is this thing, t to the 6i plus e to the tj plus 2 t e Oh, what did I do? Oh, what? I went to, what did I do? Okay, that was really weird. I went to like a different screen. Duty, E, 2 to the power of 2t, K. And we're also given that R, R of 0 is I plus J plus K. So first, what I would do is translate the vector form. So it's really the same steps. Translate the vector form. So again, when we're doing math, at least in academia, or at least from my experience, usually it's to find the pattern and exploit the pattern. And so if we find the pattern, we exploit it. So here we have R prime of t. Here we just take out the I, the J, and the K. And then we're good. We're Gucci. Okay. And then for R of 0, well, let's break that down. I is this vector. We add it to J, which is this vector. And we add it to K, which is this vector. And so we get 1, 1, 1. That's it. Okay, what's the next thing? We want to integrate, right? So here we integrate R prime of t. And this should give us, oh, okay. Let me write it the way I wrote it before. Integrate to find R of t. Then after I'm done, usually I just check these notes. Okay, so we have the derivative. Oh, the integrating R prime of t is equal to, basically we integrate each of its components. E to the t, 2t e to the power of 2t dt. Okay, what else? What else? That's it. Okay, and now we proceed to integrating. Oh, I wrote this, but and then, that's funny. Okay, I have an extra space here. Okay, before I, oh, it's too high. Is that good? Yeah, that looks good. Let's just put the spaces here. It doesn't matter. Okay, we're chilling. So let's proceed to integrating each components. So t to the 6 dt is just t to the 7 over 7 plus some constant. Next, we have, actually I'll do this in the same thing because this one's easy. Integrating, I don't know why that's not working. Integrating e to the t dt is just e to the t plus another constant. And lastly, now this is the hard part. When we integrate this thing, first thing we can think of is putting the 2 at the front of the integral. So it's usually for me like, okay, I'm not going to worry about it. I'll just put beside the integral. Now this is what I have to worry about. dE 2t dt. So how do I integrate that? Well, there are different techniques for using integration here. So maybe for me, I can see this as a product of two functions. So maybe I'll do an integration by parts. So again, another Calc 2 thing, but integration by parts, usually I would use it when I have two things here that are multiplying. And really my purpose is to get rid of this integral. That's it. So, okay, the way I'm gonna do this is, okay, I'm gonna I'm gonna assign my u and my dv. So there's pretty sure there was a format. The logarithm inverse algebra. Okay, so really this is just an art. I pick a u and a v. Let's say this is my u. Then the others is my dv. So the idea is if I pick a u and a dv here, and when I integrate this thing, I will get there's a formula I memorized. Let's see if I were to do it again. I get something like, so I have a u and a dv. I get a v du times v. Actually, I forgot. Let me double check my notes. It was an integration by parts. So usually, yeah, these are some things I just forget. So I'm just looking at my calculus 2 stuff. Uh, Integration by parts. I think it was this one. What was this? Oh, there we go. Oh, there we go. UdV is equal to UV minus VDU. And then there's a function for it. If I'm given two functions, then I just multiply both functions. And then I get this, I subtract this to an integral of the second function times the derivative of the first function. So yeah, and then I do this formula here. And this works. Tried, tested, worked. Cool. Okay, so let's quickly do that. So this is something I surprisingly forgot. So UV minus VDU. Okay, cool. Now let's see how we do this again. So my U, or actually, yeah, we can take this out. So my U here is T, and my dV here is e to the 2t dt, right? So my du is my derivative of t, which is 1, right? So it's just 1. Um, what else? Oh yeah, and then my v, oh, holy moly, is the integral of this thing. Yeah, see, that's why integrals are so long. So the integral of this thing is, so if I get, so this is 1/2 e to the 2t plus some constant that I don't know. Yeah, this should be 1/2. Why? Because if I get this, the derivative of this thing, I get 2t. Oh, but I put 2t down. Okay, how am I gonna figure this out? I take the derivative of this thing. So, yeah, if I take the derivative of this thing, I do the same thing here. So this is chain rule times 2. Okay, and then I got 2e2t. So I have yeah, I need a 1/2. Yeah. Because now, if I take the derivative of this thing, then I get 1/2, leave it alone, e to the 2t, so that's chain rule. And then I multiply it by 2. Yeah. So it's 1/2 e to the 2t, yeah. Okay, let's do that. E to the 2t. We'll assume there's some constant there. We don't need to explicitly say, okay, there's a constant here. Uh, okay, wait, let me double check. Wow, I'm surprised. Yeah, I pick a u, and then my du is, oh, so I do a dx. So in this case, the other one I do a dt. And then my dv, see, this is the power of nodes from last quarter. Yeah, my dv is the rest of this thing, and my v is just, yeah, integrating sine, which is negative cosine. Because if I get the derivative of negative cosine, I get sine. But yeah, okay. So, yeah, I should be able to do this here. Where was I? Oh, I lost myself. Okay, here. Yeah. So in this case, this is supposed to be a dt. Cool. Oops, my bad. Yeah, something to remember is integrating. Okay, so I have this thing. Now I want to use my formula. So u v minus v du in an integrate in the integral. So this is t times, oh, okay, I can combine that. I can say t over 2 e to the 2t. I can do that. Or I can do 1/2 t e 2t. Totally fine. I subtract to an integral of v. So 1/2 e to the 2t and du, so dt. So this makes sense because I know I have a dt here. And so I put the 1/2 outside because I don't need it. And now I'm left with this thing. Another integral that I'm trying to get rid of. 2t dt. So I have this other integral I need to get rid of. So we're getting there. So usually that's how integrals work. We're peeling and we're peeling until we get something. So now we have to solve this integral. This is, we already solved it. 1/2 e to the 2t plus some constant. I don't know how many constants I put. I put like 1, 2. Did I put 3? No, I put a 4 because I know I'm gonna put a 3 here. But honestly, it's any constants. Cool. Okay, so we have these, and yeah, because if we take the derivative, we get this thing exactly. We take the derivative of this thing, we get this exactly. Okay, cool. So let's use that. Okay, so yeah, so here we have t 2 e to the 2t minus 1/2 of this thing, e to the 2t, plus some constant, let's say c3. So this is t to the 2, t over 2. How many times have I said t? 1/4 plus some constant. And there we go. Whew. So that was a long peel of derivatives. So there, we were able to get this thing. And now we multiply that by 2. So we have 2 of that thing, 2 of this. So t over 2 e to the 2t minus 1/4. Then I get another e to the 2t. And then plus c3. So I can just put that somewhere here. Oh, I have a c3 here. I have another c3 here. Maybe, I mean, it doesn't really matter. I can say this is c4. No, I can say that's c5, then this is c4. Doesn't matter here. They could be any number, honestly. It could be A, B, C, D, E, F, G. Um, but yeah, so that's how we integrate that thing. And we can still simplify this thing. So we can say this is d e to d minus 1/2 of e to d plus c3. So we can do that. Phew. Okay, so we peeled the heck out of that integral. And so now we can find, yeah, now we can find r of t. Okay, I'm just gonna, let me say I used integration by parts here because this is so messy. Maybe for practice, we could do more differentiation and integration. But usually that's just the heart of calculus. It's these two things. Okay, so now we have my vector function. Now we're going to calc 3. So my vector function, which is, so we don't consider the constants anymore. I mean, actually we do, my bad. So we have t to the 7th over 7. So that was my x component, comma. My y component is e to the power of t plus c2. And lastly, I have my, what was it? T to t minus 1/2. Oh, I can actually simplify. I could simplify this. Yeah, I could say e to the 2t, t minus 1/2. I could do that. So another thing I realized I could do to simplify, to make it cleaner. So I have e to the 2t, t minus 1/2 plus another constant. Phew. Okay, so now we've found that. Next thing we want to do is find the constant C1, C2, C3. And we want to use that information that we got. So again, we want to find constants. And here we named them C1, C2, and C3 using what we're given. The given info we have was R of 0, which has 1 for each component. So let's just plug that in. So when t is 0, so 0 over 7, 0 to the 7th over 7 is 0, plus c1 is equal to 1. Well, this tells us that the first constant is equal to 1. As easy as that. The next one. So we have e to the 0, which this is 1, plus c2, the constant, is equal to 1. So this tells us c2 is equal to 1. To 0, I mean. Oh, that's funny. Now my thing's not working. It's still loading. So my second constant is a 0. And lastly, this really long integral. At least it simplified nicely though. Plus c3. And this will give me c3 is, okay, this makes it a 0. This is a 1. Oh, I forgot. This is also a 0 because this is a t. So we have 1 times negative 1/2. So that's just negative 1/2. Plus, oh, I forgot to add the thing. So this is equal to 1. Yeah, everything's equal to 1. So this is minus 1/2 plus the constant is equal to 1. And so C3 is just 1 plus 1/2. And so that's 3 over 2. Right? Because this is 2 over 2 plus 1/2, 3 over 2. And so that's my C3. So C3 is 3 over 2. So yeah, this is more calculus 2 stuff. Long, very, 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 very long computations. So now from here we can find our vector, our position function, our position vector function. So we have r of t, which was t to the 7th over 7 plus c1. My c1 is 1. Oh, I forgot to add the arrows. My bad. E to the 7th over 7 plus 1, comma. Then we do e to the t plus c2. My c2 here is 0, so I don't add the 0 anymore. And lastly, e to the power of 2t, t minus 1 half, plus 3 over 2. And so that's my whole vector function. Wow. So that was yeah, the tricky part is integrating. Now I hope I didn't get it wrong. If I did get it wrong, that's funny. But yeah, I hope I didn't. Unless there was an easier way. Could I have done it with a U substitution, maybe? No, I couldn't have. Yeah, I don't think so. Yeah, this is definitely using the technique of integration by parts. Yeah, and then UV minus VDU. Okay. Then I multiplied the thing. Um, where did I get the 1 half though? Oh, because I integrated e to the dt. Yeah. Uh, yeah. Then I get this thing. Then I ended up with this, and then I simplified it even more. Yeah, right here. So yeah, this is really more in the heavy integral side. Okay, let's see if I got it. I don't. I'm doubting myself, especially with this long of a computation. It's really um, it's really easy to mess up. But we don't really know that, so let's okay. And then we have e to the t for my y component. In my z component, we have, so this is the long one, t minus 1 half, I believe. Is that what I got? Let me see. Minus 1 half, yeah. And then some constant, which was, in this case, derivative. And the t. Okay, this should be it. If not, that's okay. There's always time. Oh, got it. Okay, yeah. Okay. That was a breathtaking, actually. Okay, now what we're gonna do is we're gonna proceed immediately to the next lesson, which I wasn't prepared for actually. But yeah, let's just go for it. So here let's just go for it. So 13.3, and this is all about, forgot where was it? 9. So this is all about, oh, not that. So yeah, we talked about derivatives and integrals of vector functions. Now we're going to talk about arc length and curvature. Now, I did do a little bit of review on arc length, but they not good spelling. Arc length and curvature. Okay, cool. So let's talk about this. And basically, bottom line, when you're getting an arc length of a curve, you're getting the length of the curve. That's it. And there's a formula to do that. And it basically requires integrals. So we want to make use of integrals to get the arc length. of a curve. Now here maybe, I don't know, my guess, we're doing it on vector functions, right? So actually maybe before we move exactly to this topic, I might do a little bit of review on arc lengths of functions. So not even vectors, on functions. Where was this? Yeah, these were my calculus 2. There we go. Calculus 2 stuff. There we go. So the arc length of a curve is basically the length of this thing. If we're given some curve, then we're basically just getting the length of it. And okay, some formulas. Usually there's this one formula that just helps. Okay, we derived all of it. Boom, there's the formula. So the length of a curve is the integral from bounded by a to b. And then we're doing a square root of 1 plus the derivative of that function squared dx. That's basically what we're doing. So let's say, I don't know, if we're given some curve, let's say, I don't know, that, let's say that's f of x. And to get the length of that whole thing, well, we want to get from a all the way to b. And we take the derivative of this thing, put it to the power of 2, add 1, square the whole thing, integrate. And that's the length. So maybe it has something to do with that. Okay, that's enough of that. Let's move on to actually applying it to vectors. So let's immediately talk about arc length. So for arc length, well, yeah, in that section, we define the length of a plane curve with parametric equations x equals f of t and y equals g of t. Okay, I can't see. X equals f of t and y equals g of t. And t is in between a and b inclusive as the limit of lengths of approximating polygonal paths, and for the case where their derivatives are continuous. And so we arrived at a particular formula. So I'm just going to go straight. I'm going to hop into the formula. So the formula is just going to be its arc length, which is L, the integral from a to b, square root of, so the formula here is a bit different actually. Yeah, for vectors. So it's going to be f prime of t squared plus, what in the world happened? Okay. Okay. Never mind. Yeah, so f prime of t squared plus g prime of t squared. Now, you might be asking, where in the world did f of t and g of t come from? I thought we were talking about f of x. Well, in this case, because we're talking about vectors, and vectors have parameters, right? So we have parametric equations. For x, we have some function of f. And for y, we have some function of g, and they're all in terms of t, right? And we also say that the t, the parameter t, is in between a and b inclusive, so including a and b. Yeah, and then there's so we can use that, or another notation is just the Leibniz notation, where we just say, okay, yeah, there's just a difference in notation. I'm gonna put both because I want to, but they mean the same thing basically. Honestly, my opinion, I'd use this. But if you guys know this better, I know some of my classmates know this better because of the dx/dt. If this is easier, go for it. Use this. But yeah, when I'm doing this, I would probably use the first one. Because that's, yeah, when I first started calculus, I was exposed to this one. More on this one instead of the second notation. Anyways, So the length of a space curve is defined in exactly the same way. So here I'm going to show a figure. Let me just take a screenshot and show a figure of some space curve. So here we're not talking about the plane curve, we're talking about a space curve. And so in this plane curve, it has a vector equation, right? Suppose that's how we identify a space curve. We use a vector equation to describe it. And for a plane curve, we use a function. Has the vector equation. We're going to use R of t maybe. Yeah. R of t is, well, R of t has composite, not composite, component functions. F of t, g of t, h of t. These could be any, honestly. So these are parametric. They have parameters t, where we have bounds a and b. Yeah, or equivalently, we can say x is f of t, y is g of t, but they mean the same thing. Z is h of t. So when you separate them, then they're not parametric equations, which is why if you have parametric equations, you can immediately convert it to a vector function. And vice versa. If you have a vector function, you can rewrite it in terms of their x, y, and z. So yeah, here, so here we say, or we assume that the derivatives of each component function, f prime, g prime, and h prime, are differentiable and integrable. So in this case, they're continuous. At least that's from my experience with these calculus courses. The basic, at least, is if you want a function to be differentiable or integrable, then they are continuous functions, meaning no holes, no gaps, no nothing of that. No nothing. Okay, so here we're saying if the curve is traversed exactly once as t increases from a to b, right? Then it can be shown that its length, oh, let's actually write this. Yeah, this looks. So we're saying if the curve is traversed exactly once as t increases from a to b. Yeah, usually when we're doing an integral, the b is the upper boundary. So usually b is bigger than a. But well, based on my experience from my previous Calculus 2 course, well, that's not necessarily the case. But we'll not get into that. If we get into that, I'll probably explain it, but not now. Then it can be shown, then its length is as follows. So we have L for the length, and this is an integral from a to b. So we know this is a definite integral because it's defined. It has boundaries, a and b. And we have the square root of f prime of t squared. So this is actually the same as this one, but here we're just adding the h. That's it. So f prime of t plus g prime of t squared plus h prime of t squared. That's it. And there's another notation for it, which is the Leibniz notation. So I'm just going to write it out for those who prefer this notation. So we have dx we have our x, we have our y, and we have our z with respect to t. So these are the same. Can we say this is 2? Okay. Now, we notice that both of the arc length formulas can be put into a more compact form. Well, how do we know that? Well, we can just say L. This is actually easier. L is basically, so an integral bounded. It's just the length of this thing, dt, right? We can say that. Because here, when you notice, we're actually just getting the distance formula. So this is technically the magnitude of our vector function, right? So it's just a more compact way of doing it. But yeah. Okay, he made it. Okay, he explained that part. I don't need to. But basically, they're equal. Okay, let's move on to example 1. As much as possible, I want to get into the examples. Because usually that's where all the math improvement happens. Okay, so we're being asked to find, so based on these formulas, maybe we're being asked to find the length. So immediately we think of that formula. The length of the arc of the, the circular helix. So we did talk about helix before with vector equation. So here's what we have to focus on. It's the given vector equation, maybe. Is it going to be shown? Not sure. Oh, it's shown. Crap, we use that then. So we have the given vector equation cosine di plus sine d j plus, okay, oops, my bad. I use my eraser. Let's put that here maybe. Okay, plus dk. And we're also given points. So from the point, so here's our bounds maybe, to another point, 1, 0, 2 pi. So again, we use the formula that we got. So here's basically just use arc length formula. Which is just our L, which is the integral from a to b of the length or magnitude of our vector function. Oh, our derivative, so our tangent vector, dt. Okay, let's see. So I guess we find, okay, maybe first thing I want to do, my R of t, I want to make it into vector form. I don't like working with not vector forms. Done. Okay, now I convert it to R prime, so I take the derivative of each component. So this is negative sine. Okay, this one's easy. And then cosine. And then 1. And then, what else can we do? We want to get its length, right? So maybe, okay, let's do that. Let's get its length then. R prime of t. The length is square root of this thing squared plus this thing squared plus 1 squared. This will give me, what will this give me? Well, this is the same as cosine squared of t plus sine squared of t, which is just 1. That's a trig identity. So this is square root of 2. Now, the last thing we need to do is find a and b. So how do I do that? Well, we can use the 2 points that were given. These 2 points. So probably one is A, one is B. But basically, the arc from those 2 points is described by the parameter interval 0 less than or equal to t, less than or equal to 2 pi. Huh. Is it just the distance between those 2 parameters? Or those 2 points, I mean? Uh, looks like it. By the parameter and okay. So we're given, okay, cool. Huh, really? Uh, what? Or is the textbook making it complicated? uh, tell me it's just their length, right? Parameter. What did it say? Oh, no, actually, I don't know. Um, traverse. What? So the arc from a point to another point is described by the parameter interval. That's interesting. Okay, I don't know how to do this yet, so I'm gonna say I ask because I don't know, obviously. But I think it's just their lengths. This should just be their lengths. If not, then I'm gonna think of something else. Yeah, I think it's just their lengths. Mm, oh. Oh, I see, I see. So I have to plug in these 2 points in my position vector to get the parameters. Yeah. So I don't assume immediately. So I'm gonna say uh find A and B. Okay, wait. Let me let me I'm gonna say find so this first step is find R prime of t. Okay, now I know where to find it. So next thing is you want to find boundaries A and B. So for A and B, actually, we have to plug in these points for my position vector. And then I find the corresponding t. So what I'm trying to say is from this point, or to get to this point, what t should be in my vector function, right? So maybe, okay, let's look at that. So cosine of t is equal to 1, right? And so here my t is arc cosine of 1. And I can put this in radians. Yeah, this is 0, right? And then the next part, 0, 0. So I'm going to try it again. So I have sine of t. I'm looking there when I have this. Then I now have sine of t, which is equal to 0. And so my t here is again 0, right? And lastly, I look at t is equal to 0. So I have these. T equals 0. This is given 1, 0, 0. And then now I look at the next point, and I again use my vector function to find my a. So my a is actually 0. So here, I'm saying my a is equal to 0. Now I need to find my b. So my b is, okay, I look at my next point. So here I again have cosine of t equals 1. So my t is again 0, right? Then I look at my sine of t, which is again 0. And I find again that t equals 0. And then I look at my other one. I have a 2 pi here. So t is 2 pi. Okay, well, t is 2 pi. Can I find that? Maybe, can sine be 2 pi? Well, yes, sine can be 2 pi. Can sine be 2 pi here? Well, actually, yes. Or can cosine be 2 pi here? Yes. So I can say another point where my t can be satisfied is this point. So that's my b. And now I have the whole thing. So I just solve for it. So my L is the integral from 0 to 2 pi. And I take a square root. Oh, I don't take a square root. I get the magnitude. So the magnitude here is, I'm pretty sure I solved it already. I got square root of 2, yeah. dt, or what was it? dt, yeah, dt. dt, yeah, my formula says dt. And I get, so yeah, there again, another formula. When we're given some constant, so this is just a fun fact, AB, C is a constant, the dx, I don't care. This is just C times the upper boundary minus the lower boundary. Or you could do the normal integrating thing. If you do the normal integrating thing, well, it's gonna give the same thing actually. CB minus A, that's what this is. But yeah, if you integrate this thing, well, it's gonna be a 0, right? Oh no, if we take the, what was this? Some constant, we take its, we integrate it, well, we got CX. CX, B, A. And then here you get CB minus CA. And here we can isolate C, which is the same thing. So yeah, just a quick formula there that works for both. Okay, so here I got square root of 2 times 2 pi minus 0. So I just made it 2 pi, and that's it. That's my length. I mean, that should be my length. Done. Okay, so here we can say a single curve can be represented by more than one vector function. Huh, what does that mean? Oh, okay. It's a new thing. So here we're saying, oops. We're saying a single curve. So we have a curve in space. We'll call it C. Can actually be represented by more than one So this is one I didn't expect. Because, yeah, initially I thought you can only represent it by one vector function, but I guess not really. The curve. So, yeah, examples of this. Well, we have this vector function, R1, which has these components. T squared, t to the 3. And then this is in between 1 and 2. But this could also be represented by a different vector function. So that's what it's saying. And here we put u. It could be any, honestly. They just made it u, so that's different. This is e to the u, e to the 2u, and e to the 3u. Now, how are they able to do this? That's the interesting thing. And basically, the condition is that u is in between. Ooh, this is oddly specific. U is exactly in between 0 and ln of 2. Why 2? Huh. And so we can actually connect these parameters. We can say p is equal to e to the u. Oh, and then we derive from that. So we say that e squared is just e to the u squared, which is e to the 2u. And then e to the 3u is just d cubed. Okay. So equation 4 and 5 are parametrizations of the curve C. If we were to use equation 3 to compute the length of C, of that curve C, using equations 4 and 5, we would get the same answer. This is because arc length is a geometric property of the curve and hence is independent of the parametrization that is used. So I guess that makes sense. Yeah, if we use an arc length on this guy or this guy, we'll get the same answer. So we'll get the same number here. And I'm not gonna try it anymore. You guys can try it. Okay. So now we're moving on to the arc length function. Wait, I wonder what was the first one. Okay. The arc length function. Okay. So the arc length function. So suppose C is a curve given by a vector equation. And the vector equation is on R of t again. And it has 3 composite functions here. Why am I saying composite? Component functions. So this is an IJK format. And the condition is T has boundaries A and B inclusive. And we're saying its derivative for R prime of T is continuous. And C is traversed. Exactly once. Okay. As T increases. So here we're just doing a little bit of background on everything. We're just trying to be really precise here. From the A boundary to the B boundary. And so we define its arc length function to be this guy here. So arc, okay. Let me go ahead and write the formula of the arc length function. So the arc length function is as follows. We have some s of t. So now it's a function. A to the t. Oh, so here we're not given a b boundary anymore. That depends on us, where we want it to stop, right? And here I do um, a different parameter, maybe u, du. So it's the same thing, but this time we're 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 not setting a fixed boundary, a fixed upper boundary. And so that's that. We can do it in Leibniz notation, doesn't matter. So again, it's gonna be dx du, dy du, and dz du. Okay, it's kind of messy, but hey, it's cool. Okay, so we can do it in that notation as well. Not gonna focus too much on that though. Yeah, so s of t is the length. So here we're saying s of t is the length of that curve C, or the length of part of C, so not all of it, between R of A and R of T. And if we differentiate both sides, so if we take the derivative, right, if we differentiate, let me quickly write this, both sides, we get so S, oh, my bad. So S prime of T is just the length, R prime of U, right? Or R prime of T, it doesn't matter. Okay, the textbook said R prime of T, so that's pretty weird. Oh no, actually it's because of the fundamental theorem of calculus. So yeah, we take the derivative of this guy and then the derivative of this thing. If we take the derivative of this thing, then we're just replacing T to U. That's a thing in fundamental theorem of calculus, part one, because there are two parts to it. So let's just talk about it real quick. But if we have an integral from a to t, and we have, or actually a to x, why not? Let's just do x. So this is a real valued function. So oh my goodness. Yeah, a to x. And then we have f of t, dt. Well, if we take the derivative of that, well, we would get f of x. That's it. That's fundamental theorem of calculus part one. So again, another calculus 2 lesson. So yeah. So it is often useful to parameterize a curve with respect to arc length. So that makes sense. Because arc length arises naturally from the shape of the curve and does not depend on a particular coordinate system or a particular parameterization. That also makes sense, yeah. Yeah, I mean, we could have like any shape. So we just have to get the arc length reactively. It's not like we already know what this exactly, but we have to react to it. So if a curve R of t is already given in terms of parameter t, and S of t is the arc length function, then we may be able to solve for t as a function of x. So yeah, if we're given a parameter t, and we're also given the arc length function, then we can solve for t in terms of s. So we can do the other way around. And then the curve can be reparameterized in terms of s. Huh, that is confusing. Okay, thus if S is equal to 3, for instance, R of D of 3 is the position vector of the point 3. Oh, so we can reparameterize. Oh, we need to do an example of that. Let me see how that works. Actually, I'm going to write it out and see if, let's see if we get. So basically, we're saying if a curve, so we have a curve, right, which has R of t, has that vector function. Let's say this is given. So we're given this. Our parameter is t. And we're also given that S of t is the arc length function. Okay, let me see if we can dissect this, because when I read it, I found it confusing. So here it's saying, okay, I'm going to write it in my own words, see if I get. So it's saying we can solve for t as a function of S. So what that is saying is, well, we can say t is equal to t of S. So we're actually given the arc length here. So we're given the arc length S, and now we can find t. So we just have to plug in the S to get t. Okay, so far so good. What else? Okay, let's do a next paragraph, just so we can split the ideas. Then we're saying, after we get that thing, the t, we can reparameterize. We can parameterize again. So the curve can be reparameterized in terms of S. How does that look like in notation? So here this is, so okay, in terms of S, by substituting t. So we have R. So R is again our vector function, is basically R of t of S. So that's what that's saying. We have S, and then we can get t, and then we can use that t to find a new vector function. So for instance, if t is equal to 3, or no, my bad, if S, so here we're given S is 3, then R of t of S, so in this case t of 3, right? And we have a time out of that, is the position vector. So that's the new vector, the new position vector. Of the point 3 units of length. Yeah, I have to look at an example to really get this. 3 units of length along the curve from its starting point. So that's really cool because we can reparameterize, and now we know the length of the curve. Because we know S. S is 3. Okay, let's actually see that in action before I eternally yap. So let's do our next example here. So here we reparameterize the helix R of t is equal to cosine of t I. Yeah, I want to see how this exactly works because when I read it, I'm like, what? Plus sine of t j plus dk. So again, it's a circular helix. With respect to arc length measured, okay, let me write that. I'm not just gonna, so with respect to arc length measured by, or measured from, not by, measured from a starting point. So 1, 0, 0 in the direction of increasing t. Okay, that is really confusing at first. Let's see. Well, so the first thing that we want to do is find our s, right? So the first thing we want to do is find arc length. So we want to find s of t, which is just the same as s. So how do we do that? Well, we have this formula here where the derivative of s is exactly the length of r prime of t. And so we can use that, right? So from actually this connects to our previous example, but basically, where was my first example? Here. It's actually the same thing as this one. So yeah, we got r prime of t, right? So here we're saying s of prime t, s prime of t is exactly the length of r prime of t, which is square root of 2. So s prime of t is square root of 2. And so we use that formula to get s of t. So s of t, which is equal to, or you can just say s. So s of t is exactly, where was it? Here we go. A to t. So that's 0 to t of the length dt. Or du? I forgot. Oh, it's du here, but yeah, it's, I mean, it could be a dt. Doesn't really matter. Sure, we can make it a du. Doesn't matter. And this is exactly square root of 2 times t. And now I have my s and my t. And now again, what I can do based on what I've read is I can get a function in terms of s. So from here I can say, okay, if s is equal to square root of 2 times t, then t is s over square root of 2, right? So I'm going to say find t in terms of s. I'm going to say t of s is exactly s over square root of 2. So now I've switched the rules. Now my s is my input, my t is my output. And then from here, I can say reparameterize So how do I reparameterize? Well, I use my R of t of s, or my nu t. So I should get a new position vector. So I'm going to say R of t of s, which will give me a new thing. So this is, or I could just say R of s square root of 2, and this will give me a vector. So instead of t, I plug in s over square root of 2, basically. So I get, what is it? Oh, here, cosine t, sine t, and t. So I get cosine s square root 2, sine s square root 2, and s square root 2. Right, so that's the only difference I got. So that's how I reparameterize. So I got something. So now I have a function or a vector function in terms of its arc length function. So like a function inside of a function. So that's cool and all. Okay. What else? What else? Okay, I have a couple of. Oh, I have a lot of examples. Oh, oh my goodness. I have more examples. Okay, let me just fight through it. Okay. Phew. Okay. Let's go ahead and look at curvature. So for curvature, wait, actually, wait. Let me just check. How long is this thing? Yeah, it's pretty long. Okay, actually, before I move on to curvature, I might stop the video here. I might. Let me just double check. Because that's really weird. Yeah, it's super weird. Because I might just move on to the exercises. I don't think most of what the mm, length of curve, intersection, curvature. Okay, I have a curvature. So I am gonna talk about curvatures. Okay, so I am gonna talk about curvatures, but I'm not gonna talk about. I don't think so. No, I don't think I talk about. Um, okay, because my exercises are weird. Because we never went over um the normal and binormal vectors. Or no, I think we did for a bit. Yeah, and then goes over torsion, which I think is a physics thing. Um, but yeah, okay. You know what? I'm just gonna talk about it in this video. I mean, yeah, it's okay. I'll just talk about it here. I'm gonna go until at least curvature, and I'm gonna move on to exercises. Okay, so about curvature. Um, okay, so okay. So a parameterization RFT is called smooth on an interval I if its derivative is continuous, right? And if its derivative is not zero on I. So that's what that means. Okay, wait, actually, okay, my bad, my bad. Before, okay, maybe before I thought about curvature. I'm gonna do some exercises on. Yeah, okay. Here's what I'm gonna do. I'm gonna do exercises on the length of a curve, and then once I get to a curvature example, I'm gonna go directly do a curvature example. Yeah, so I'm just gonna go for it. Yeah, so change of plans. I'm gonna do some exercises on lengths of curves. So yeah, okay, let's just go do it. So the first thing, or the first question, is I want to find the length of the curve. So let's quickly do that. So we have r of t, which is equal to these components, 1 over 6 t cubed. Okay, and those are our conditions. So again, when we're looking at this thing, well, we want to use our arc length formula. So that formula is, again, the length, the integral from a to b of their derivative squared, right? Okay, let me quickly check if I'm getting it right. Uh, yeah, so it's just there. No, actually, I don't need to do that. Yeah, I don't need to do that. Yeah, I could just directly find the length of it. Okay, let's just do that. Okay, so that's what I'm gonna do. Um, yeah, I still use the same formula though, but I find the length of the derivative vector. I call it now the derivative vector, the tangent vector, and that's it. So now I plug in, or I solve for what I need to know. So I get the derivative of 4t, so that's 4, plus the derivative of t squared, so that's 2t squared. And then let's say, because for a length, I'm supposed to get a number, right? Or am I just messing around and I don't actually know? Oh, because here I get cosine t and then, oh, okay. So this is interesting. Yeah, yeah, because here now, I'm not sure what to do about this. Yeah, so I don't actually get a number here, which is funny. Um, okay, cool. Let's just go for it. So, okay. Uh, let's take the derivative of this thing. So 1 over 6, and then this will be, put the 3, we get 1/2 t squared. Yeah, so we got t squared over 2 squared. And then this gives me a weird thing. So it gives me square root of 16 plus 4t squared plus t to the 4th over 4. So it gives me that thing. Um, yeah, damn, that's yeah, that's something. Okay, and then we're supposed to get a and b. So okay, so to get, actually it's just, yeah. Find A and B. No, actually, we know what A and B are. A and B is 0 to 1, so we know what that is. Yeah, so A is equal to 1. A is equal to 0. B is equal to 1. Cool. Now we solve for it. So the length, 0 to 1. This thing, dt. Now, how do I solve this integral? Whew, okay. That's tough. I haven't done this in a while. But usually the trick to doing this is finding something that can be squared. So it's usually a completing the squares method or something along those lines. Yeah, usually we're trying to find something squared here so that we can get rid of the square root. So that's okay, let me check. Yeah, that's something I find hard to do. Um, but that's cool. Let's see if we can find some tricks here, maybe. Because there's a calculus 2 problem. Um, yeah, so something like this. Uh, oh, I managed to do that. That's okay. And there's one other thing here. Oh, this is y to the sixth. Yeah, it's honestly it's one of these things where there's no exact like formula. You just have to. Okay, let me let me see. Mm, oh my goodness. Okay, this doesn't work. That's fine. Um, okay. Yep. We calculate the magnitude. Okay, so we can factor out a 1/4 out of this thing. Oh, and then we do a completing of the square. Yeah. Okay. So I could factor out a 1/4 here. So this is 0, 1. I factor out a 1/4. And so I get t to the fourth plus t squared plus 16. So that's a 4. Or no, that's a. Oh, crap. This was 16. Yeah. Yeah. This was 16. 16t squared. And then this was 64. Yeah. Okay. dt. So here I'm just factoring a 1/4. And I can actually put it out. So I can put out a 1/2 there. Um, so I can put 1/2, 0 to 1. Now what do I do with this? Well, I can complete the square. So this is going to be t fourth. Let's see. 16t squared plus 64. Okay, so this is going to be t squared maybe plus 8. This would be nice if there was an actual formula. This is t squared. Let's see. This is like a nice um nice thing though. So let's just go for t fourth. 8t squared, so 16t squared. Yeah, and then 64. Yeah. So it's yeah. So this is the same as this thing. So algebra stuff. So we got t squared plus 8 squared. And now we can take out the square root. So I get 1/2 integral, and I get t squared plus 8. Done. Phew, the hard part's gone. So that's usually the tricky part here when we're doing an arc length. And then now integrate like so. So we have 1/2. We have d cubed over 3. We have 8d. Then I evaluate this thing. So I get 1/2, 1/3 plus 8. So that thing minus another thing. Oh, it's just 0. So it's just this thing. So I got 1/2. And then this is 25/3. I hope I'm right. Then 25/6. Yeah. So usually the tricky part here is doing evaluating integrals. Okay, number 2. So here now we're being asked to find again the length of the curve. So let's quickly do that. So this is r of t. Oh, we're given a vector function here. Cosine 90 I plus sine of 90j plus 9 ln. Oh, so it's composite functions. 9 ln cosine t. Okay. And the condition is, or our bounds, is 0 and pi/4. So again, we apply the formula that we know. We use the arc length formula. So here maybe you can start by solving the derivative and getting the magnitude maybe. So let's quickly do that. So here, actually this should be fine. Use arc length formula. Okay, so here we get the derivative and find its magnitude. So let's quickly do a square root. Oh yeah, before I do that, let me convert the vector form. My position vector. So this is cosine of 90, comma, sine of 90, comma, 9 ln of cosine of t. Okay, now we just get their derivatives. Ooh, this one's tricky. So we get derivative of this thing, and then squaring it. So this is negative sine, negative 9 sine 90. Should be fine, right? Yeah, because I make this a sine, it's a negative, and I multiply a 9. Okay, we add, we get the derivative of this, so it's 9 cosine 90. So here I'm using just chain rules. Then here I get a 9. What's the derivative of this thing? Let's take it step by step. So this is 9. I leave the 9 alone. ln, so I do a 1 over cosine t. And then I do a chain rule for cosine of t. So that's going to be cosine, negative sine of t, right? Then I have a negative 9 sine of t, cosine of t. Sine over cosine is tangent. Yeah, so I get a -9 tangent. Wow, I'm practicing all of my calculus 1 and 2 stuff. Goodness me. Okay. Great. Now we've taken derivatives. Done. That should be frightening. Okay. Uh, what was the next thing? Okay, this doesn't look clean for a solution. We can clean it up more. So let's say, yeah, let's clean it up more. So here we can say this is positive, so 81 sine squared of 90 plus 81 cosine 90. And I can actually clean this up even more. Yeah, let's keep doing that. Cosine squared of 90. And we have another thing here, plus 81 tangent squared of t. Great. And now we can factor out the 81, and we can actually put it outside. So we can do that. So if we have a 9 square root of, so we can factor it out. We have sine squared 90 plus cosine squared 90 plus tangent squared t. And funny enough, this is actually just 1 plus tangent squared of t. And 1 plus tangent squared is secant squared. And this is just secant t. So it's a really, that's clean as hell. Okay. Right? Because sine, how do I do that? Sine cosine is 1. If I divide everything by cosine, I get tangent plus 1 equals secant. So 1, oh, this is squared, by the way. So I get tangent squared, I get secant squared. So that's how I know. And then secant squared, here I completely remove the square root, which is really, really nice. That's what we want to do. We want to remove that square root. And we managed to do it. So that's really helpful. Okay, and then now we have our A and our B, so we're chilling. Our A is 0, and our B is pi over 4. So that was a nice simplification. Now I can just plug it in. So we have L, the integral from 0 to pi 4th. Then we have 9 secant d dt. And now I can just, well, okay, maybe I can take out the 9 here. And now I can just evaluate this integral. So we integrate the thing. So we have 9 of, how do we integrate the secant again? This is something I don't memorize. I need a table of integration. Do I have that? Or no? I don't think I do. Okay. Let me quickly check my previous. There's a formula for it though. Okay, so it's natural log of secant plus tangent. So natural log of my secant plus my tangent. So something I maybe have to put in the notes because I totally forgot this thing. And I apparently used it here. Cool. Okay, now what do we do here? evaluate the whole thing. So we have, can I do this without, let's see. So ln of secant of pi fourth plus tangent of pi fourth, right? So that thing minus ln of secant of 0 plus tangent of 0. Can I get a number now? Let's see. So secant, oh, I don't have a secant. Cool. I just use 1 over, for secant, I could use in my calculator 1 over cosine of pi fourth. So it's cosine pi fourth. Oh my goodness. So it's something I don't know. How about the zeros? Cosine of 0 is 1. 1 over 1, so this is 1. What is this? Tangent of 0 is 0. So the whole thing is 1. ln of 1 is 0. So this whole thing is 0. Okay, I'm just trying to do it without having to evaluate everything. This one, so secant of pi fourth. I get cosine pi fourth, which I don't know. So I'm quickly gonna look at the trig table, which I probably should have in my notes as well. Pi fourth of a cosine is 1 over square root of 2. Oops, my bad. Yeah, so this is 1 over square root of 2. So yeah, secant pi fourth is just square root of 2. So something I wouldn't actually know. So square root of 2. Tangent pi fourth is 1. So this is square root of 2 plus 1. Okay, then I get, yeah. So I basically get 9 ln of square root of 2 plus 1. And that's my arc length. Okay. Very very annoying integrals. I don't like it. Okay. Did I get though? Okay, good. I got, luckily. So we have 9 natural log of square root of 2 plus 1. Let me hit submit, see what happens. Okay. Uh, okay, for number 3, here we let C be the curve of intersection of parabolic cylinder. So x squared is 2y, and surface. So yeah, the first one was a parabolic cylinder, because z is 0, yeah. And the surface, 3z equals xy, so that's a quadric surface. And here we're being asked to find the exact length of C. From origin to a point. And the point we're being given here is 4, 8, 32 over 3. Okay, cool, let's do it. So, what is this? 9, 10. Okay, cool. Let's just go through it. Yeah, this is tricky. We have a curve of intersection and the surface. So we actually have two surfaces here. And we need to find the curve of intersection and find that exact length from 2 points here. So we have 2 points. So the idea is we need to find, yeah, so here we're given two surfaces, right? And so we need to find that exact curve. And then once we find that curve, we need to find the length of that curve of intersection from 2 points. So this is two problems in one. Okay, let me quickly see how to do it. Yeah, we need the parametric equations. Okay, so the first idea is to find parametric equations for curve C, right? And so here we can say, oh, x squared is 2y. And so we say y is x squared over 2. If we let x be t, then we have y is t squared over 2. Now we need to find z. Yeah, then we have this. Then our z is just t cubed over 6. So those are our parametric equations for that curve C. Okay. I can write it in vector form. Then we find its arc length. So we get the derivative of each. So we get 1/2 t, and then we get uh t squared over 2. T. Um, uh, our, what? Okay, let me see. So here we get the length. So we got 1 plus t squared plus t to the fourth over 4. Okay. Now we want to find the exact t where we will get these points, origin to that. So here we're finding A and B. Yeah. So my A is the origin. Or yeah, from the origin, what t do I need? Well, of course, that's just 0. So R of 0 will give me 0, 0, 0, which is exactly the origin. So here my A is equal to 0. And for my B, well, I need some point where if I plug in a t, I'll get 4, 8, 32 over 3. So let's say my 4 is equal to t here, right? So it might be a 4. So this is 4. And then I plug in a 4 here. 4 squared is 16, divided by 2 is 8. Exactly what I need, an 8. And then my last point, 4 cubed is 4 times 4 is 16 times 4 is 64. 64 over 6. And I can divide both by 2, so I get 32 over 3. So yeah, my B here is supposed to be a 4. And I just use the length. So 0, 4. Yeah, here we want to factor out. So maybe we factor out a 1/4. So here we have a 4. Here we have a 4t cubed. And here we have a t to the fourth dt. Then we can continue factoring this out. So this is a 1/2, 0, 4. And then here maybe, let's see, this 4. Well, this looks like a t squared plus 2, right? I can square that. So I get t squared times itself. So I get t to the fourth. I add, and then I get, yeah. So this is t squared plus 2 squared dt. And I get 1/2, 0, 4. I got t squared plus 2 dt. So it's really completing the squares technique. And I can just integrate from here. So I get 1/2, 0, 4. Or I can actually integrate it directly. So I have t cubed to the third plus 2t is 0, 4. So I get 1/2, 4 cubed over 3 plus 8. And then I get 4, 64 over 3 is that thing? It's not. So I get 64 over 3 plus 324, right? Yeah, and I got 88 over 3. Goodness me. Then I can cancel. I get 1. I get 44. So I'm left with 44 thirds as my final answer. Okay, I'm gonna stop the video there because I realized it's way too long. But yeah, I hope you guys learned something. And yeah, I'll see you all in the next one.